Prove that the torque acting on a body, the torque acting on a rigid body, which rotates with an angular acceleration, alpha, is tau equal I alpha, where I is the moment of inertia of the body about the axis of rotation. Tau equal I alpha, where I is the moment of inertia of the body. Prove that the torque acting on a rigid body which rotates with an angular acceleration alpha is tau equal I alpha, where I is the moment of inertia. In diagram, this is a rigid body of mass capital M which rotates about the axis AB. M is the mass of the body if we consider first constituent particle of mass M1, which is at a distance R1, from the axis of rotation. R1 is the distance of the first constituent particle from the axis of rotation, and it is also the radius of the circular orbit in which the first constituent particle revolves around the axis of rotation. First particle has the tangential on this first particle, a force F1 acts inwards and linear acceleration is A1. But this first particle of mass M1 rotates about the axis of rotation AB with an angular acceleration alpha which acts vertically upwards, and torque tau1 is also acting vertically upwards, provided the body rotates in anti-clockwise direction in horizontal plane about the axis of rotation AB. Similarly, this is the circular orbit in which the second constituent particle of mass M2 revolves. This is the circular orbit in which the second constituent particle of mass M2 revolves. R2 is the perpendicular distance of the second constituent particle of mass M2, and this particle revolves in anticlockwise direction in this horizontal circular orbit. On this particle, a force F2 acts, the particle revolves in anticlockwise direction. On this particle, a force F2 acts inwards, and there should be linear acceleration in the direction of force F2. This is A2 is the tangential or linear acceleration, and F2 is the force which is acted on the body inwards. And acceleration A2, linear acceleration A2 is in the same direction as that of the force F2. And the second constituent particle revolves with an angular acceleration alpha. And torque acting on this particle is tau2, which is in the upward direction. That means angular acceleration alpha will be in the same direction of torque tau2. Similarly, we can consider a circular orbit in which nth particle of mass M1 revolves in anticlockwise direction. Rn is the perpendicular distance of this nth constituent particle from the axis of rotation. On this particle of mass Mn, a force Fn is acted, and there should be linear acceleration An in inward direction, and angular acceleration of this particle will be alpha, and torque will be tau n. Tau n is the torque acting on this particle, and this particle revolves with an angular acceleration alpha. In this case, linear accelerations are different, that is A1, A2, An, all are acting inwards, but angular acceleration of all the particles will be same, that is alpha, alpha, alpha. when a rigid body of mass m rotates about its own axis of rotation AB, about its own axis of rotation AB, under the action of a torque, when a rigid body of mass m rotates with an angular acceleration alpha about its own axis of rotation AB under the action of a torque tau, the constituent particles of masses m1, m2, mn, the constituent particles of masses m1, m2, mn will rotate. Constituent particle of masses will rotate with the same angular acceleration alpha. Here we have to add, that is, with an angular acceleration alpha. That means rigid body of mass m rotates with an angular acceleration alpha under the action of torque tau, and the constituent particles of masses m1, m2, mn will rotate with the same angular acceleration. Therefore, torque acting on the rigid body is tau equals sum of torque acting on the constituent particles. That means tau 1 plus tau 2 plus tau n. Tau equal tau 1 plus tau 2 plus plus tau n. It should be tau n. That is equation 1, expression of torque, where tau 1 equal torque is the product of perpendicular distance and force R1 F1. Tau 2 equal R2 F2 tau n equal Rn Fn are the torque acting on the constituent particles in vertically upward direction, provided these constituent particles revolve in anti-clockwise direction along horizontal circular orbit. Therefore, tau equal R1 F1 plus R2 F2 plus Rn Fn. R1 in place of force F1 we can write m1 a1 means mass into acceleration plus R2 m2 a2 plus plus Rn mn an. That is the expression of torque acting on the rigid body, or total torque acting on the n number of constituent particles, which is equation 2, where a1 is the linear acceleration, which is the product of angular acceleration and the perpendicular distance. A1 equal alpha r1, a2 equal alpha r2, an equal alpha rn are the linear accelerations of the constituent particles. Of the rigid body, and these linear accelerations will be acting in inward direction, and therefore what will be the expression of torque tau will be r1 under bracket m1 alpha r1 plus r2 under bracket m2 alpha r2 plus plus rn under bracket mn alpha rn. Now we can take common alpha. Therefore tau equal alpha under bracket m1 r1 square plus m2 r2 square plus plus mn rn square. Therefore tau equal alpha I. So under bracket, the term under bracket can be denoted by I, where I equal m1 r1 square plus m2 r2 square plus plus mn rn square. That is the sum of product of the mass and the square of perpendicular distance of the constituent particles, which is the moment of inertia of the rigid body about the axis of rotation AB. So therefore tau equal I alpha means torque is the product of moment of inertia and angular acceleration. Tau equal I alpha. Hence the torque acting on the body. Hence the torque acting on a body is equal to the product is equal to the product of the moment of inertia is the product of the moment of inertia and its angular acceleration. Product of moment of inertia and its angular acceleration. Hence tau equal I alpha proved.